In this tutorial 18, we are going to discuss on topic ideal gas equation, pressure, speed and kinetic energy of the gas. Okay, so we are going to divide into part 1. So this is the first question for part 1. A gas cylinder is fitted with a safety valve that releases gas when the pressure exceeds 3.2 times 10 to the power of 5 Pascal. So the cylinder is filled with 14 kilogram of an ideal gas at 3.2 times 10 to the power of 5 Pascal and temperature of 300 Kelvin. So calculate the mass of gas that remains in the cylinder when the temperature increases to 360 Kelvin. Okay, so that's mean the pressure is fixed at 3.2 times 10 to the power of 5 Pascal because every time we release the gas, so that the pressure remain the same. We don't want the pressure to exceed this value. Okay, so the cylinder is filled with 14.0 kilogram. So this is the mass for this pressure, okay, and the temperature. So all this is M1, P and T1. Okay, so then we are going to calculate the mass of the gas that remains in the cylinder when the temperature increases to 360 Kelvin. So this will be temperature 2, okay, and this will be mass 2. Okay. So we are going to use this formula. So the formula we choose is with the mass. Okay, PV equals to M over molar mass RT. So we choose this one and we form two equation. Okay, so the first equation, the pressure, okay, and then the volume remain the same because the gas cylinder is fitted with a safety valve. So the volume will be the volume of this cylinder. And then the mass 14, R is 8.31 and the temperature for mass 14 kilogram is 300. Okay, given here T1 and the molar mass. We are going to molar mass will be the same because we use the same gas trap in this gas cylinder. Okay, so this is equation 1. So this is the M, we cross multiply, so you get this M. So for the mass 2, we are going to find for temperature 360 Kelvin for temperature 2. So this is mass 2. So the molar mass will be the same. We are going to substitute this into here later. Okay, now we equate these two. This is M, molar mass is the same. So we equate them, cancel the V, and we can get M2. So M2 is 11.7 kilogram. So that's the answer. Okay, next we are going to do question 2. A helium balloon has a volume of 2.5 times 10 to the power of negative 3 meter cube at a pressure of 120 kilopascal and a temperature of 300 Kelvin. So calculate the number of moles of helium atoms in the balloon, then the number of helium atoms, and see the mass of the gas in the balloon if the molar mass of helium is 4 gram per mole. So molar gas constant R is 8.31 joule per mole per Kelvin and Avogadro number is 6.02 times 10 to the power of 23 per mole. Okay, so volume given, pressure given, and temperature given. So the number of moles is N, small letter. Okay, so from this equation, you are given PVT and then N. So we choose PV equals to nRT equation. Okay, we substitute the pressure, the volume, and the N is, we are going to find N. Okay, R is 8.31 and temperature 300 Kelvin. So we get N equals to 0.12 mole. So this is question A, answer, the answer for question A. For question B, we are going to find number of helium atoms, capital letter N. So that's mean we can choose this equation. So from N here is number of mole is N number of molecules over number of Avogadro number. Okay, so we substitute this N and the Avogadro number, and we get number of molecules is 7.2 times 10 to the power of 22. So this is helium atom. So this is number of atoms. Okay, next we are going to do question C. The mass of the gas in the balloon is if the molar mass of helium is 4 gram per mole. Okay, so for mass we use N equals to M over molar mass. Here, molar mass. So N equals to mass of the gas divided by molar mass. Okay, so M mass of a gas is equals to molar mass times number of moles. So 4 times 0.12 and we get 0.48 gram. Okay, so that's the answer. Next we do question 3. 20 gram of hydrogen and 24.0 gram of helium are mixed together in a container that has a volume of 0.50 meter cube. The temperature is 350 Kelvin. So calculate the number of moles of hydrogen. Okay, so you are given mass of hydrogen, mass of helium, and volume. Okay, the container has volume 0.50 meter cube. So temperature 350 Kelvin. So for number of moles of hydrogen, we use symbol N, subscript H. Okay, so the formula we are going to use, you are given MV T, so that's mean we are going to use this one, N over N number of mole equals to mass of the gas divided by molar mass. Okay, for the hydrogen, so NH equals to mass of hydrogen is 20 gram, okay, divided by molar mass is 2 gram per mole, given down here, 2 gram per mole. Okay, so you get number of moles for hydrogen 10.0 mole. Okay, for the number of moles of helium, we use the same formula. So we use symbol N subscript H for helium. So 24 gram for mass of the helium, mass of the gas helium, and divided by 4, the molar mass for the helium is 4 gram per mole, and you get number of mole is 6.0 mole. Okay, next question. See the pressure inside the container. So what is the pressure inside the container? So the pressure inside the container will be the general pressure here. The container consists of hydrogen and helium gas. So that's mean we use total of number of mole here. So the N will be a total of 10 mole plus 6 mole. R is 8.31 and the temperature of both mixed gas helium and hydrogen will be 350 Kelvin, and the volume inside the container, the volume of the container is 0.50. So you get the pressure 9.3 times 10 to the power of 4 Pascal. Okay, lastly, the question is to find pressure due to the hydrogen alone. So just now, total pressure. So the pressure due to the hydrogen alone, so we use the same formula. So the formula is PV equals to nRT. Okay, but R constant and temperature is also constant. It's the same container, and the volume also the same. So that's mean the P directly proportional to the N. From this formula, P is directly proportional to N. So we can use P hydrogen over the P total or P final. P total is this one, 9.3 times 10 to the power of 4 Pascal. Okay, and then the number of mole for hydrogen divided by the for P total will be the mix of the gas. So not number of mole H plus number mole of hydrogen and number of mole for helium. So we substitute the values. This one P 9.3 times 10 to the 4, total of number of moles 10 plus 6 mole, and then for hydrogen alone is 10 mole. So we cross multiply, we calculate pressure of the hydrogen gas is 5.8 times 10 to the power 4 Pascal. So that's the answer for D. Okay, next question. Which of the following is not an assumption of the kinetic theory of gases in an ideal gas model? Okay, so the answer is B. The mass of a molecule is negligible as compared to the mass of the gas. So if we refer to the equation just now, one of the equation, PV equals to M mass of the gas divided by mass of the gas divided by molar mass, okay, times uh, RT, okay, RT. So that's mean the mass of the molecule is not negligible, okay. So compared to the mass of the gas, so it is included. It is included in the kinetic theory of gases. So B is the answer. Okay, next question 5. The pressure P of an ideal gas is related to the mean square speed of the gas molecule by this equation. So what are represented by the N and the M? So the N is number of molecules per unit volume, okay, and then this M is the mass of one molecule. Say N is not number of moles but number of molecules per unit volume. So be careful with this equation. And then the mass here is a mass of one molecule, so it's not the mass of the gas. Okay, next question 6. The density of a gas is 1.75 kilogram meter cube at a pressure of 1.80 times 10 to the power 5 Pascal. So calculate the r.m.s speed of the gas molecule. So we have three equation of pressure. Okay, 1 over 3 density times mean square speed. Another one is 1 over 3 number of molecule density, mass of one molecule times mean square speed. So the last one, we substitute the N here, number of molecules over volume. This is number of molecule density. Okay, so we choose the first equation. Okay, from the first equation, mean square speed, we cross multiply, we get 3p over density. So the mean r.m.s speed will be square root of 3p over density. So we substitute the pressure here and the density into the equation, and the r.m.s speed will be 555 meter per second. Okay, so that's the answer. Okay, question 7. The pressure of an ideal gas in a vessel of fixed volume is P. So if the gas in the vessel is heated so that the r.m.s speed of the molecules is increased 3 times the initial value, so what is the new pressure of the gas? Okay, so the answer is 9P. So how we get this answer? So from this equation of pressure, so we choose the third one because the given here fixed volume. Okay, fixed volume. Okay, so that's mean P is directly proportional to the mean square speed. So B is constant. Number of gas also constant because the gas is trapped in the vessel, right? The same volume. Okay, so we can use Pi over Pf equals to mean square speed. I is initial, equals to mean square speed at final. Okay, so we must use this P. We substitute into the equation. This P is given. Okay, P final is becomes the P final is the what we are going to find. Okay, the new pressure. So v.r.m.s squared over 3 times v.r.m.s because mentioned here increase 3 times. Okay, so we simplify, we get P final equals to 9P. So that's the answer. Okay, so done for part 2. So done for part 1. So we are going to discuss the part 2 tutorial 18. Okay, for question 8, the r.m.s speed of the molecules of a certain gas is C. When the volume and pressure of the gas are doubled, the r.m.s speed of the gas molecule is, so we have A, B, C. The answer is D, 2C. So how we get this 2C? So from the equation here, pressure, so we choose this one because volume and pressure okay of the gas are double. So given here volume and pressure, so we choose this equation. So next, this is for equation 1. Okay, let's P will become P. Okay, N V M, mass of a molecule, so will be the same for equation 2 also M. And for the P pressure is where is it? A double. Okay, pressure double, and then volume also double 2V. Okay, N remain the same. Then the mass of one molecule also the same. So CF will be different. So C is the speed, the r.m.s speed. Okay, final. Okay, equation 2. Then we use ratio. We simplify first equation 2. So cross multiply 2 times 2, we get 4p, 1 over 3, and then n over v remain the same, m, and then cf squared. So this is equation 2. So this 1 over 3 n over v and mass of a molecule, we substitute this into here. So we substitute this into here. Okay. So P over mean square speed. So we cross multiply a mean square speed. So we substitute into here, and we cancel P, and we get the relationship between CF and this C. So CF, where the questions want r.m.s speed, so we square root both sides. So we get r.m.s speed, square root of 4 mean square speed. Okay. So the mean square speed, square root of mean square speed is C. So square root of 4 is 2. So the answer is 2C. Okay, so the answer D. So next we do question. Okay, there is another method using the formula of r.m.s speed here. So there are four equations for r.m.s speed. Okay, so we choose PV equals to nRT, and r.m.s speed is 3 kT over m. So this is mass of one molecule. Okay, so we substitute the pressure to P, and then volume to V. Double here, the volume and pressure double. So nRT is constant. Okay, then 2 times 2, 4 PV equals to nRT. And for the r.m.s speed, 3 square root of 3 kT over m. So uh, the T is PV. From here we substitute into here. So PV over NR. PV equals to nRT. So that's mean the T is PV over NR. So we substitute into T here. So now the equation from equation 1 and equation 2, we use ratio. So C over r.m.s, and then all the constant we can cancel out. So we get 1 over square root of 1 over 4. So we cross multiply, so we get r.m.s speed is 2c. So this is the second method. Okay, next we go question 9. A cylinder of volume 0.09 meter cube contains an ideal gas at 100 degrees Celsius and 8 times 10 to the power 4 Pascal. If the mass of 1 mole of the gas is 0.034 kilogram, r.m.s speed of the gas molecule is, so the answer is B, 5.23 times 10 to the power of 4 meter per second. So how we get this answer? So look at what information given. So you are given V, you are given temperature and pressure. And the number of mole is 1, and the molar mass is 0.034 kilogram. So this for number of mole is 1. So therefore this value is also a molar mass. Molar mass. So we are going to find r.m.s speed. So from the equation here, we choose PV equals to nRT. Okay, for 1 more. And the r.m.s speed is 3 square root of 3 kT over m, mass of one molecule. This is this m is not the same as this m. This m is mass of a gas, and this m is mass of the one molecule or one atom of the gas. Okay, so we substitute P, pressure given, volume given, okay, and then N, This n, for if we use this one, this n is not 1 mole. This n is not 1 mole. So if we use this equation, the temperature is 1 degree Celsius convert to Kelvin. So it's not 1 mole, it's 2.32 mole. But we don't need to use this equation actually. We are going to find r.m.s speed, so we straight away use this equation. Okay, where the molar mass, actually we can use molar mass, but if we want to use this equation, so the mass of one molecule here, we can use molar mass over Avogadro number, okay, for 1 mole. So we, from the equation, these two equation, n over Avogadro number equals to mass of one molecules over molar mass. So the mass of the gas here, this m, is 1 over Avogadro number times the molar mass, 0.034. Okay, so we use this equation to get the mass of one molecule. So we get this answer. But actually we can use this equation straight away, 3RT over molar mass. Also we get answer B. So if we this one no need to use, just to show you that the this n is 2.32 mole, so not 1 mole, mass of the gas, molar number of mole of the gas. Okay, so we can use this straight away actually. R is 8.31, so temperature is 100 plus 273 divided by molar mass. So this is understood as molar mass. So we straight away get the answer B, 5.23 times 10 of 4. So actually there are many methods to use. Okay, so next question 10. The pressure of a gas is in a vessel is P. The r.m.s speed of the gas is C. So the gas is heated at a constant volume until the pressure is double. So what is the new r.m.s speed of the gas molecule? Okay, you are given P, you are given C, and it's a constant volume, and the pressure is double. So for final pressure 2P, so we are going to find the final r.m.s speed. Okay, so from this equation, we choose the first one where P is directly proportional to the mean square speed. So density of the gas is the same because it's the same gas trapped in the vessel. Okay, so P over 2P, okay, initial over final, P over 2P, pressure is double. And then initial r.m.s speed is C divided by final r.m.s speed squared. Mean square speed. Sorry, this is mean square speed. Okay, we cross multiply, cancel the P, and we get 2C squared equals to C final squared. So we get C final equals to cert 2C. So this is the answer. Okay, that's the last question, 11. Air at a temperature of 30 degrees Celsius contains a mixture of hydrogen and oxygen molecules. Find the mean translational kinetic energy of the hydrogen and oxygen molecules. B. Calculate the r.m.s speed of the hydrogen molecules and oxygen molecules. So given that mass of hydrogen molecules is 3.32 times 10 to the power of negative 27 kilogram, and oxygen molecule is 5.32 times 10 to the power of 26 kilogram. Okay, temperature given. We are going to find kinetic energy. So this is mass of hydrogen, this is mass of oxygen. Okay, so from this equation, r.m.s speed, we are going to use, because we are going to find kinetic energy, so this V speed, we can use this equation. So kinetic energy is half mv squared. So for the mean translational kinetic energy, so we need to find V first. So the V we choose this equation, 3 kT over m. So this m is mass of one molecule. Okay, so 3 kT, cancel the m, so we get 3 kT over 2. So this is kinetic energy, 32 times kT. So K is the Boltzmann constant, temperature at a constant, temperature convert to Kelvin and divided by 2. So we get 6.27 times 10 to the power of 21 joule. Or you can memorize straight away formula of the kinetic energy. That day I give you the formula for kinetic energy. So if you cannot remember the formula of kinetic energy 3 over 2 kT, so you can use the r.m.s speed if you memorize this better. So you can use half mv squared, substitute the r.m.s speed into here. Okay, and then question B, calculate the r.m.s speed for the hydrogen and then r.m.s speed for the oxygen, CH and then CO. Okay, for the r.m.s speed, so we can use this equation. K kinetic energy is 6.27 times 10 to the power of 21, to the power of negative 21, and then half mass of the hydrogen is given here, and then the r.m.s speed squared. So we cross multiply and we get r.m.s speed 1940 meter per second. So convert to three significant figures. Write in the three significant figures because here given in three significant figures. The data given is in three significant figures. Okay, for CO speed, r.m.s speed for oxygen, you do the same, but this time you substitute the r.m.s speed of the oxygen, the mass of the oxygen, 5.32 times 10 to the power of negative 26. Okay, so you cross multiply, you get r.m.s speed of oxygen 486 meter per second. So that's the answer for r.m.s speed for the oxygen. Okay, done for tutorial 18. Part 2. So both part 1 and part 2 done. Okay, so bye bye.